I'm Mark Arines, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 21. Given a number n, consider the set of all its proper divisors. That is, consider all of the numbers which divide into n, excluding n itself. Define d of n to be the sum of these proper divisors. If, for some values a and b, we have d of a equals b and d of b equals a, with a and b non-equal, we call a and b an amicable pair. And we call each of a and b individually amicable numbers. An example is given to us by the problem description. The proper divisors of 220 are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. The sum of those divisors is 284. Conversely, the proper divisors of 284 are 1, 2, 4, 71, and 142. The sum of these numbers is 220. So 220 and 284 form an amicable pair. In fact, 220 is the smallest amicable number, so in some sense, this is the simplest example of an amicable pair. The problem description asks us to find the sum of all amicable numbers less than 10,000. The first question we might reasonably ask is whether or not the constraint that a is not equal to b is redundant. That is, are there any numbers such that d of a equals a? The answer is yes. We have a few examples of numbers satisfying this property, and we even have a name for them. If a number is equal to the sum of its proper divisors, we call it a perfect number. The first perfect number is 6, whose proper divisors are 1, 2, and 3. The second perfect number is 28, whose proper divisors are 1, 2, 4, 7, and 14. We know of the first 10 perfect numbers, and it's an unsolved mathematical question as to whether or not there are an infinite number of them beyond that. On top of that, all 10 perfect numbers we know about are even, and it's an open question whether or not there can ever be any odd perfect numbers. We don't want to count perfect numbers when we're looking for amicable numbers, so the extra check that a is not equal to b is in fact necessary in this case. Let's get started and write some code. We'll start today in Ruby. The first thing we need is a function to get the sum of the proper divisors of a given number. As we've discussed before, Ruby has a very mature streaming API through its enumerable module that allows operations happening on sequences or array-like structures to flow in a natural and object-oriented way. We start with the range of numbers from 1 up to and excluding n. The triple-dotted Ruby constructs a half-open range which excludes its upper bound. Then we filter this range to only include divisors. Finally, we sum the result. Now comes the question. How do we identify if a number is an amicable number? The problem description told us how to identify amicable pairs. Specifically, two distinct positive integers a and b form an amicable pair if a is equal to the sum of proper divisors of b, and vice versa. It went on to say that a number is an amicable number if it's one part of some amicable pair. But what if we're just given one of the two numbers? Suppose we're just given a. The first thing we have to do is find a candidate for b that might work as the second half of our amicable pair. If this a is going to be an amicable number, there must be a b such that d of a equals b and d of b equals a. So if this is going to work out, the only possible choice for b is d of a, the sum of proper divisors of a. So set b equal to the sum of proper divisors of a. Then check that a and b are non-equal. If they're equal, then a is a perfect number, not an amicable number, so we return false. If they're not equal, then check that the sum of proper divisors of b is equal to a. Also note that the name of our isAmicableNumber method is actually amicable number question mark. The question mark is part of the method's name. By convention, in Ruby, we end methods which return a boolean with a question mark. This doesn't change the behavior of the method semantically, it's just for the human reader. Now for our main block of code. We take the range of all numbers from 1 up to and excluding 10,000. Perform a filter operation to keep only the amicable numbers, sum the result, and print it. We can neaten up the amicable number predicate a bit, and experienced Ruby developers have probably already spotted how we can do so. This pattern of if a condition is false, return false, else do something, is just short-circuiting behavior, and it's identical to the behavior of the built-in AND logical operator. So we can replace our entire if statement with a simple logical conjunction. And now we have our solution in Ruby. This week, we'll be writing our final solution to this problem in APL. Specifically, we'll be using dialog APL. We've alluded to APL multiple times before. APL is the pioneer of the tacit array-oriented family of languages that includes J and Jelly, both of which we've used before, as well as K and A+, which we'll undoubtedly use in the future. That is to say, APL puts a huge emphasis on arrays and point-free style programming. Like J, arrays in APL are written by simply concatenating numbers and separating them with a space. This is an example of a 3-element array whose elements are 1, 2, and 3. And like all of the array-oriented programming languages we've seen so far, APL happily broadcasts its scalar operations across arrays. So if we use the plus sign on two arrays, we'll get the pointwise sum of the arrays. 1, 2, 3 plus 4, 5, 6 equals 5, 7, 9. Since 1 plus 4 is 5, 2 plus 5 is 7, and 3 plus 6 is 9. We have access to all of the usual arithmetic operators: plus for addition, minus for subtraction, multiplication sign for multiplication, and division sign for division. Now would be a good time to interject. Whereas J made it a design goal that all built-in operators can be typed on a standard, modern US keyboard, APL had no such constraint. APL is an older language, first introduced in 1966. And in the 70s, the language was released with a custom keyboard specifically designed to be able to type all of these unique characters. As you can see, it's not just the mathematical operators like multiplication and division signs. We also have more exotic operators like this upward triangle with a line through it that you don't see in so-called conventional mathematical notation. The APL programming language predates Unicode as we know it today, and many of these symbols were added into the Unicode standard for compatibility with APL. The triangle I just mentioned is Unicode code point 234B, named APL Functional Symbol Delta Style, and it's part of an entire subsection of Unicode devoted to APL functional symbols. So if we're going to use this language, we can't shy away from exotic character sets. Aside from the exotic character set, APL is a lot like J. So as long as you've seen episode 3 of this series, you should feel somewhat at home in APL. Our basic data types are the character, written enclosed in single quotes, and the number, written as you'd expect. There's no distinct integer type in dialog APL. Then, of course, like any good array-based language, APL defines the array. Like J, arrays in APL are potentially multidimensional. We call the number of dimensions of an array its rank. So a rank 1 array is a simple vector, or list in Python terminology. A rank 2 array is a matrix, and so on. We say a simple character or number which is not enclosed in an array has rank 0. And we call things of rank 0 scalars. As we've already seen, arrays are written simply as elements juxtaposed together. There's no mandatory comma delimiter in APL, so if we want an array of numerical literals, we simply write them next to each other with spaces in between. As a bit of syntax sugar, a sequence of characters enclosed in single quotes is considered a character array, so we can write one-dimensional character arrays in a syntax somewhat like strings in another language. That is, these two forms are equivalent. Each produces a rank 1 array of characters, where the array has length 3. Note that a single character literal written on its own is still a scalar, not a rank 1 array. The built-ins available to us in APL are divided into two categories: functions and operators. Functions are denoted using single characters. Functions can take either 1 or 2 arguments. We call a function which takes a single argument a monadic function, or simply a monad. We call a function which takes 2 arguments a dyadic function, or a dyad. We say that the valence of a function is how many arguments it's taking. So a function has either monadic or dyadic valence. Many of the functions in APL are overloaded and do something different depending on whether they're used monadically or dyadically. For example, we already saw the minus sign, which, when used dyadically, subtracts 2 numbers. When used monadically, the minus sign returns the additive inverse, or negative, of the input. Notice how negative numbers are printed in APL. That's not a font malfunctioning, that's actually a minus sign slightly above center. Specifically, in modern Unicode, that's code point U plus AF, the macron character. If we want to write a negative number literal in our code, we need to use that as the prefix, not a standard minus sign. By the way, as you can see here, function arguments are passed to a function in APL the same way they're passed to a verb in J. If a function is being used monadically, we pass the sole argument on the right. If the function is being used dyadically, we pass the first argument on the left and the second argument on the right. The division sign divides 2 numbers when used dyadically, but when used as a monad, it returns the multiplicative inverse, or reciprocal. The addition sign adds 2 numbers in its dyadic form. In its monadic form, it returns the complex conjugate of its input. If you don't know what complex numbers are, don't worry. We won't need those today. The multiplication sign multiplies 2 numbers dyadically, but when it's used monadically, it's the signum function, which returns the sign of the input. That is, if the number is greater than 0, we get 1. If it's less than 0, we get negative 1. And if it's equal to 0, we get 0. The infamous delta style, or triangle with a line through it, in monadic form is called grade up, and it performs a sorting algorithm, though you may not know it from a glance. When we apply grade up to the character array taxicab, we get this array of 7 numbers. Can you explain this output? Think about it for a minute. Here's a hint. APL is 1 indexed by default, meaning the first element of an array has index 1, not index 0. If we wanted to sort the characters in the word taxicab, we'd put the 2 A's first, then the B, then the C, I, and T, and finally X. And that's exactly what APL has done for us, it just gave us the indices rather than the values. The 2 A's are at positions 2 and 6. The B is the last character at position 7 in our array of length 7. C is at position 5, I is at position 4, T is at position 1, and X is at position 3. APL has done the work of sorting the array. It's just given us the indices rather than the values in order. If we want to get the actual values back, we can simply use this permutation vector as an index into our original array. There are lots of built-in functions in APL, but for the sake of keeping this video under 30 minutes, we'll focus on the ones we actually need today. Comparisons are done as you'd expect. The dyadic equal sign is the equal operator, which compares two values for equality. APL doesn't have a dedicated Boolean type, so equals returns 1 to indicate truth, and 0 to indicate falsehood. Note that the equal sign is not used for assignment to variables. We've already seen one example of how to do that. To assign a value to a variable, we use the left arrow token. Like most operators, equal broadcasts over arrays. If we pass it two arrays of the same length, the result will be an array of zeros and ones, where each position in the result indicates whether or not the corresponding elements of the two inputs are equal or not. If given an array on one side and a scalar on the other, it returns an array of the same length as the original, comparing each element to the scalar in turn. Equal has no monadic variant. It's an error to try to apply equal with no left-hand argument. Match, written as a triple equal sign, is a variant of equal, which doesn't broadcast over arrays. That is, match will always return a single scalar, 0 or 1, indicating whether the two arguments are exactly identical or not. There are also logically inverted variants of both of these functions. Not equal, written as a Unicode equal sign with a slash through it, is a broadcasting inequality comparison, and not match, written as a Unicode triple equal sign with a slash through it, is a non-broadcasting inequality comparison. Moving on, the dyadic forward slash is called replicate. It takes an array of numbers on the left-hand side and any array on the right. A new array is produced where the elements from the right-hand array are repeated the number of times indicated in the left-hand array. That's a mouthful. Let's see an example. Here, our right-hand argument is an array of 7 characters, spelling the word snowman. Our left-hand argument, correspondingly, is an array of 7 numbers. In the result, we'll take the first character once, since the first element of the left-hand array is 1. Then we'll skip the second character, since its corresponding position is a 0. We take the third character twice. Then we skip the fourth, fifth, and sixth, and take the final character once. In the end, we get the word soon. As a degenerate case, if our left array is a Boolean array, that is, if our left array consists of only zeros and ones, then replicate doubles as a filter function, keeping the elements corresponding to a 1 and discarding those that correspond with a 0. The down arrow as a dyad is called drop. The right-hand argument must be an array, and the left-hand argument a number. The first n elements of the right-hand array are dropped, and the new array is returned, where n is, of course, the left-hand numerical argument. If the left-hand argument is negative, then values are dropped from the right instead of the left. Remember that we write negative numbers with a preceding macron, not the hyphen minus character on your keyboard. The other functions we'll need today are pretty straightforward, all things considered. The dyadic vertical bar is called residue, and it functions as our modulo operator in APL. Note that residue takes its arguments in the opposite order than our usual modulo operator. So x residue y actually calculates the remainder when we divide y by x. Monadic tilde is our logical not function, which maps 0 to 1 and 1 to 0, effectively inverting a Boolean. Logical not produces an error if applied to any number other than 0 or 1, though it does broadcast over arrays of numbers as you'd expect. We have access to the other logical operators as well. The logical AND is written as a Unicode wedge, and the logical OR is written as a Unicode V. Both are dyadic and broadcast over arrays. Finally, monadic iota is called index generator. Given an integer argument, it produces an array of all of the integers from 1 up to the argument inclusive. That's all the built-in functions we'll need, but before we move on, we need to talk about operator precedence. Our J program was simple enough that we sort of glossed over this at the time, but array-based languages have a very particular approach to the order of operations, in that they don't really have one. Typically, mathematically speaking, we define an order of operations, and that defines what order we evaluate expressions in. Consider the following mathematical expression. Our typical rule in basic arithmetic states that multiplication should happen before addition. So we multiply 5 and 2 and get 10, then we multiply 2 and 4 and get 8, finally 10 plus 8 is 18. Using the typical rules of arithmetic, we get 18. If we were to plug this into a language with left to right semantics, such as Rebol, then we'd get 48. That's because we just start on the left and go to the right. 5 times 2 is 10, then add 2 to get 12, finally multiply the entire thing by 4 to get 48. However, APL actually does the opposite. In APL, we effectively move right to left. So if we start on the right, we multiply 2 times 4 and get 8, then we add 2 to get 10, finally we multiply by 5 to get 50. This might seem like an odd rule, but it works fairly intuitively for array-based semantics. The general rule, as phrased by APL and most of its derivatives, is this. A monad always absorbs everything it can to its right. A dyad always absorbs everything it can to its right, and as little as necessary to its left. That is, when we write a function name, either a monad or a dyad, we can assume that everything to the right of the function's name is its rightmost argument. Full stop. Of course, as in any self-respecting programming language, we can override this with parentheses if it's not the order of operations we actually need. Now, a minute ago, I said that APL has two kinds of built-ins, functions and operators. Functions are limited in one respect. They can only take values as arguments. Other functions aren't really values in APL in the same sense that they are in a functional language such as Haskell. So if we want to use higher order functions, that is, functions that produce other functions or take other functions as arguments, we need a different class of built-ins. We call built-ins which take one or more functions and produce another function, operators. There are only two operators we'll need today. The first is each, written as a lone diaresis. This isn't a quotation mark, it's a diaresis. Each takes a function on its left and produces a new function which applies the original to each element of its eventual argument. Each can be applied to either a monadic or a dyadic function, and it produces a new function of the same valence as the original. That is, it takes monads to monads and dyads to dyads. Each is sort of like our for loop in APL. Many functions in APL, I'd go so far as to say most functions in APL, broadcast over arrays by default. So even in situations where you might need a for loop in other languages, you often won't require each in APL. However, some functions do have special behaviors on arrays other than typical broadcasting, and in particular, it can be useful to control broadcasting of custom functions that we ourselves write. We'll see an example of that when we get back to the Project Euler problem in just a few minutes. The other operator we'll need is a bit of an odd one, in that it's overloaded with a function. When we use the forward slash as an ordinary function, it's dyadic replicate, but we can also use the forward slash as an operator, and as an operator, it works the same way as the corresponding adverb in J. That is, the forward slash takes a dyadic function on its left and returns a new monadic function that reduces the original over an array. We can use this to sum an array, or take the product of all elements of an array. In fact, the forward slash reduce operator makes writing a factorial function incredibly simple. We can do it in just 3 characters, times slash iota. We've got 3 characters, but this is really just 2 monads. The first monad is times slash. Remember that the slash took a dyad, times in our case, and gave us a new derived monad. The second monad, of course, is iota, called index generator. So we take our input, 4 in this case, and pass it to index generator. That produces a one-dimensional array of all of the integers from 1 up to 4, inclusive. Next, we apply the times slash monad. This takes each element of our array and multiplies them together. The net result is the product of all of the integers from 1 up to our input. That is, the result is our factorial. Now let's talk about trains. Normally, when we want to apply a function, we put an argument on its right, and if it's dyadic, we also put an argument on its left. But some of the real power of APL, and indeed most tacit languages, comes out when we start chaining functions together. Trains of verbs in APL are subtly different than trains in J, but if you're familiar with J, a lot of that knowledge will transfer today. Note that chains in Jelly work substantially differently, on account of the fact that links in Jelly aren't overloaded by their valence, whereas most functions in APL, and most verbs in J, work both monadically and dyadically. When APL encounters 2 or more functions in a sequence that are not immediately being applied to arguments, it treats them as a train. This is a complicated sort of function composition, but it isn't always just running the functions in order like the dot operator in Haskell. If APL encounters 2 functions in a row, it treats them as an atop composition. This form really is just function composition. If the atop form is used monadically, then the right-hand function is applied monadically to the argument, and the left-hand function is applied also monadically to the result of the first. It's as though we applied the 2 monads in order. When the atop form is used as a dyad, both arguments get passed to the right-hand function, which is used as the dyad. Then the result of that function gets passed to the left-hand function, which is still used monadically. It's still function composition, but the right-hand function gets 2 arguments in this case. Note that in an atop form, regardless of the valence of the result, the left-hand function is always applied monadically. This atop train is equivalent to explicit application of the atop operator, written as a circle with 2 dots over it, called a jot diaresis. The atop operator takes 2 functions, one to its left and one to its right, and composes them into a new function that behaves just like the 2 train we just finished describing. This is one of the differences between APL and J. In J, a train of 2 verbs forms a hook, or a with. In APL, we would write a hook using the greater than diaresis operator. A hook, when used monadically, applies its right-hand function monadically, and then applies the left-hand function dyadically, with its left argument being y and its right argument being the result of our function call. When used dyadically, the hook first applies the right-hand function monadically to the right-hand input argument, then it applies the left-hand function dyadically to x and the result of h of y. So in APL, a 2 train forms an atop, which always treats its left function monadically and leaves its right function ambivalent, which means it can be either monadic or dyadic depending on use. On the other hand, in J, a 2 train forms a hook, which always treats its right argument as a monad and its left argument as a dyad, regardless of how the derived function is used. The advantage to the APL approach is fairly obvious. An atop is a straightforward function composition in the way a functional programmer from, say, Haskell would expect it to be, whether used as a monad or a dyad. The advantage of the J approach isn't readily obvious. To see that, we need to talk about three trains. Fortunately, J and APL agree on how three trains should be treated. In both languages, a three train forms a fork. The arguments, whether there's one or two of them, are passed to F and H. Then the result of those calls are given to G as a dyad, regardless of the overall valence of the expression. Now, if we put more than three functions in a row, APL and J merely associate to the right. The rightmost three functions become a fork, and then we treat the n-2 remaining functions, including the new forked one, as a train again. So with 5 functions, the rightmost 3 get treated as a fork, and then the result of that, together with f and g, get treated as another fork. If the number of functions in the train is even, then the final train will be of length 2, and will be interpreted as a top in APL or a hook in J. In fact, this is why J chose to treat 2 trains as a hook, rather than a top. In J, a train of arbitrary even length is equivalent to a train of odd length with the same left verb, written as a left bracket, in its leftmost position. So in this way, hooks are just a special case of forks. Note that the left bracket in J is equivalent to the left tack character in APL. Finally, in a 3 train, APL allows us to replace the leftmost function f with a literal. If we do so, then that literal is treated as a constant function, which always returns the value we chose. In this way, we can sort of partially apply a dyadic function if it's part of a fork. Now we have all the tools we need. As a reminder, here's our draft from Ruby. We're counting the sum of all amicable numbers less than 10,000. Let's start by writing a sum of proper divisors function in APL. This is going to get a bit complicated, so we'll take it slow. We could write this using explicit function syntax, but we're going to get some practice with trains. That is, our sum of proper divisors function, called f, will be written in tacit or point-free style. We're not going to name our arguments. This is a function we're going to use as a monad, so it's going to take one argument on the right. That argument is our input number, and we want to return the sum of all proper divisors of the input number. First, we produce an array of all the numbers from 1 up to the input number, excluding the input number itself. We have a way to produce all the numbers from 1 up to and including the input number, called index generator, written as iota. But we want to remove the last element. Put another way, we want to drop the last element. So we use the down arrow with a -1 argument to drop the last element. Let's be very clear about what I've written here. This is a fork. It contains 3 tines. As we mentioned before, the leftmost tine of a fork can be a literal value, in which case it's treated as a constant function returning that value. So the 3 tines of this fork, all of them functions, are the constant -1 function, drop written as a down arrow, and index generator written as iota. When we eventually apply this function as a monad, we'll apply the constant -1 function and iota to the input. The constant function, of course, gives us -1, and iota gives us our array of indices, including the input. Then we apply drop, written as a down arrow, dyadically, to -1 on the left, and our index array on the right. The net result is an array of all the numbers from 1 up to, and excluding the input. Make sure you followed that explanation, because we're going to take this monad and compose it with several other functions now, using the same techniques. Remember, all of this is eventually going to be applied to one argument, the number we want to sum the proper divisors for. At this point, we have an array of candidate factors. We want to test each of these for divisibility against the original input. Our remainder function is called residue, and it's written as a vertical bar. Let's break this down. Remember that the expression in parentheses on the left is a monad which produces our candidate factors array. That work is done, and as far as we're concerned, that's just one function, not a bunch of small pieces. So this is a fork of 3 functions. The first function is our candidate factors monad we already built up. The second is residue, and the third is the conjugate monad written as a plus sign, which is basically an identity function since we're only applying it to real numbers here. This takes each of our candidate factors and calculates the remainder when that candidate factor is divided into our original input. Keep in mind how a fork works monadically. We apply our argument, which is the number we want to sum the proper divisors for, to the left and right side. The left side gives us our array of candidate factors, and the right side is effectively the identity function, so it gives us our original input back unmodified. Then we pass those 2 arguments to the residue function. The residue function happily broadcasts over arrays, so it will perform the modulo calculation for each element of the left-hand candidate factors array. Recall that the residue function has its arguments flipped from what you might be used to in other programming languages. So our dividend is on the right, and the divisors are on the left. At this point, we have an array of remainders, or to be completely precise, we have a monad which will produce an array of remainders. Now we add a monadic application of the times sign to our train. Trains associate to the right, so our fork on the right is unmodified, and this is a train of 2 functions. The left function is monadic times, and the right is our monad which produces the remainders array. A 2 train is an atop construct in APL, which merely composes the 2 functions in the typical way a functional programmer would expect. So we'll apply the right-hand function to our original input, which gives us all of our remainders, and then we'll apply the left-hand function to the result of that call. times, when used monadically, is the signum function, which gives us the sign of its input. We're applying it to an array, but that's fine because signum, like most things in APL, broadcasts. We're also applying it to remainders, which are never negative, so this has the effect of taking all of the non-zero remainders to 1 and leaving the zeros alone. That is, this is an array where each element is 0 if the corresponding number divides evenly into the input, or 1 otherwise. But of course, we want to keep the divisors, not the other way round, so we logically negate this function with tilde. We need explicit parentheses here. If we omit the parentheses, then this will be a 5 train rather than a 2 train composed with a 4 train. APL would try to treat it as 2 forks rather than a fork followed by 2 atop composition. Now we have an array of zeros and ones where there's a 1 in each position that a divisor appeared in our candidate factors array. Now I'm going to make a fork. On the left, we have an array of ones and zeros with a 1 in each position corresponding to a divisor. On the right, we simply have our candidate factors monad once again, copy-pasted for your benefit. When we multiply them with the dyadic times, this will have the effect of zeroing out all of the numbers which do not divide into our input, while leaving proper divisors alone. What we have now is an array of all the proper divisors, with an indeterminate number of zeros in between them. Now we sum the array. Plus slash is an application of the slash or reduce operator to the plus function. Plus slash is not a train. It's a single function being produced by an operator. So we have a train of 2 functions, the sum function, and the monad that gives us our divisors array. All in all, this is a monadic function that produces the sum of all proper divisors of the input. We bind that to the variable f, so we can apply it in a moment. Next, we make our array of possible amicable numbers. This should be an array of all the numbers from 1 up to 9,999, and that's just a simple application of iota. Now we're going to check whether each number is amicable. This is where the each operator, written as a diaresis, comes in. I don't know if our custom f monad broadcasts over arrays. We could find out by breaking down everything we did and seeing how each individual monad behaves on arrays, but fortunately we don't have to. By using each, we can force f to apply to each element of an array, whether or not the function is capable of broadcasting on its own. So f diaresis can be applied to arrays, and will always return a new array of sums of proper divisors for each element in the input array. So let's start by applying f, our sum of divisors function, to each element of x twice. Remember that in order for a number to be an amicable number, we must be able to apply f to it twice and get the original number back. F written twice in a row is an atop composition of 2 monads, so it's simple function composition. Then we apply that to each element of x, our array of numbers below 10,000. Finally, we compare those values to the original array, giving us an array of zeros and ones, where the ones indicate values that are unchanged after applying f twice. But this isn't all we need to do to check if a number is amicable. After all, if applying f once gets us back to the original, we have a perfect number, not an amicable one. So we want to make sure applying f once doesn't give us back the original. This gives us that array, where there are ones in every position that is not a perfect number and zeros everywhere else. You can see why APL is an array-based language now. This would all be for loops in Python or Ruby, but here we're simply storing the whole calculation in memory at once, using large arrays. Anyway, we've got 2 arrays with truth values, and we want both to be true simultaneously, so we apply the dyadic logical AND. Now, we use replicate. As mentioned earlier, replicate doubles as a filter function when the left argument is a Boolean array. So we filter our input array x by this Boolean array we've just constructed. Remember that this / is the replicate dyad, not the reduce operator we used on line 1. / is unique in APL in that it's overloaded to be both a function and an operator. So we filter our input array x by this Boolean array we've just constructed. And finally, we sum the result. There's no need for an explicit print. APL automatically prints out the result of every expression that isn't an assignment to a variable. And that's our entire program. This calculates the sum of all amicable numbers under 10,000, which solves Project Euler problem number 21 in Dialog APL. In fact, the array-based solution is significantly faster than our draft in Ruby. On my machine, the Ruby draft runs in 7 seconds, whereas the APL solution runs instantaneously. I'm not done with APL just yet. There are some more concepts I want to discuss with respect to this language, so I'll be releasing a companion video soon that solves some other problems in APL and shows some neat mathematical techniques as well. Aside from that, tune in next time on our regular schedule when we solve Project Euler problem number 22 in Elixir, the extremely concurrent beam language.